Tire production varies depending on the type of tire being manufactured: passenger car tires, motorcycle tires, off-road tires, aircraft tires, or racing tires. However, the fundamental process remains similar, involving material selection, design, and precise manufacturing techniques. 1. Raw materials and composition. Tires are made using a combination of natural and synthetic rubber, reinforcing materials like fabric and steel, and chemical compounds that enhance durability, grip, and performance. Key materials include natural rubber from rubber trees, and synthetic rubber, such as SBR and butyl rubber, carbon black and silica to improve wear resistance and traction, steel belts and fabric reinforcements, such as polyester, nylon, and aramid, chemical additives for UV resistance, flexibility, and longevity. 2. Tire manufacturing process, a design and engineering. Each type of tire is engineered based on intended use. Parameters like tread pattern, compound hardness, and sidewall flexibility vary. B. Mixing and compounding. The raw materials are mixed and processed into a rubber compound using large industrial mixers, Banbury mixers. Different compounds are formulated for tread, sidewalls, and inner lining. C. Component preparation. Tread and sidewall extrusion. The rubber is shaped into strips for the tread and sidewalls. Bead wire assembly. Steel wires are coated with rubber to form the bead, ensuring an airtight seal. Carcass and belt preparation. Layers of fabric and steel belts are cut and prepared for reinforcement. DI tire building. A tire building machine assembles all the components in stages. The inner liner is laid down for air retention. Carcass layers, textile fabric plies, are applied for strength. Beads and sidewalls are positioned. Steel belts and tread layers are added for durability and grip. The assembled structure is called a green tire, which is soft and unfinished. E. Curing and vulcanization. The green tire is placed in a mold and heated under pressure. Vulcanization chemically bonds the rubber and gives the tire its final shape, tread pattern, and elasticity. F. Quality control and testing. Finished tires undergo various inspections, X-ray scanning to detect internal flaws, uniformity tests ensuring even balance and smooth rolling, performance testing. Some high-performance and racing tires are tested under real conditions. 3. Types of tires and their production specifics. A. Passenger car tires, mass-produced with a focus on fuel efficiency, comfort, and longevity. Tread patterns are designed for all-season, summer, or winter performance. High automation is used in production. B. Motorcycle tires, require precise construction for optimal grip, lean angles, and speed stability. Radial versus bias ply structures depend on usage. Sport bikes versus cruisers. Dual compound technology is common, harder center, softer sides. See off-road and agricultural tires. Built with deeper, aggressive tread patterns for better traction on rough terrain, often reinforced with extra layers to resist punctures. Large-scale curing molds are used due to size. G. Racing tires, Formula 1, MotoGP, etc. Handcrafted or semi-automated to precise specifications. Made from soft, high-grip compounds with limited lifespan. Specialized tread designs or slick surfaces for maximum traction. Constantly developed for specific track conditions. E-aircraft tires, designed to handle extreme loads and speeds during takeoff and landing. Built with multiple reinforced plies, often over 30 layers. Requires rigorous testing for heat resistance and pressure retention. For future innovations in tire production. Airless tires, Michelin's Uptis, Bridgestone's air-free concept. Self-healing and smart tires, sensors for real-time pressure and wear monitoring. Sustainable materials, recycled rubber, soybean oil-based compounds. 3D printed tires for custom, performance-oriented designs. In-depth discussion on tire production. Tires are an essential component of vehicles, providing traction, stability, and safety. Their production process is highly complex and varies depending on the type of tire being manufactured. From raw material selection to final inspection, each step is designed to ensure durability, performance, and efficiency. 1. Raw materials used in tire manufacturing. Tires are composed of multiple materials that work together to provide strength, flexibility, and grip. The primary components include rubber compounds. Natural rubber. Derived from rubber trees, it provides elasticity and durability. Synthetic rubber includes styrene, butadiene rubber, SBR, and butyl rubber for wear resistance and air retention. Fillers and additives. Carbon black and silica. Strengthen the rubber, improving tread wear and grip. Antioxidants and antioxidants. Prevent rubber from degrading due to heat and UV exposure. Reinforcement materials. Steel belts. Enhance durability and reduce rolling resistance. Textile fabrics, polyester, nylon, aramid, provide flexibility and impact resistance. Tip 2. The tire manufacturing process, a design and engineering. Tire design varies depending on the intended use. Engineers consider factors like tread pattern for wet-dry grip, sidewall flexibility for ride comfort, internal construction for strength and stability. Using CAD computer-aided design and AI simulations, manufacturers optimize tire performance before physical production begins. B. Material preparation. 1. Rubber mixing and compounding. Rubber and chemicals are blended in large industrial mixers, for example, Banbury mixers, to create a uniform compound. Different compounds are used for the tread, sidewalls, and inner lining. 2. Component preparation. Tread and sidewalls, extruded into strips. Bead wires, coated in rubber to maintain tire shape. Textile and steel reinforcement, cut and prepared for layering. C. Tire building assembly stage. Tires are assembled in multiple stages using a tire building machine. Inner liner, a rubber sheet that ensures air retention. Carcass layers, fabric or steel belts added for strength. Bead placement, ensures a secure fit on the rim. Sidewalls positioned on both sides for durability. Tread application, determines traction and wear characteristics. At this stage, the product is called a green tire, meaning it is not yet vulcanized or hardened. Decuring and vulcanization. The green tire is placed in a curing mold at high temperatures, 300 degrees Fahrenheit to 400 degrees Fahrenheit, and pressure. Vulcanization chemically bonds the rubber, giving the tire strength, elasticity, and final shape. Tread patterns and branding are imprinted during this stage. Quality control and testing. After vulcanization, each tire undergoes rigorous inspection to meet safety and performance standards. 1. Visual inspection. Checks for surface defects like bubbles or cracks. 2. X-ray scanning detects internal structural flaws. 3. Uniformity and balance testing. Ensures even weight distribution and smooth rotation. For road testing, selective samples. High performance and racing tires undergo real-world testing on tracks. 3. Types of tires and specialized production techniques. A. Passenger car tires. Produced in high volumes using fully automated processes. Focus on comfort, low noise, and fuel efficiency. Available in all season, summer, and winter variations. B. Motorcycle tires. Require precise construction for high-speed stability and cornering. Often feature dual compound technology, hard center, soft edges. Production involves bias ply or radial construction, depending on usage. C. Off-road and agricultural tires. Designed for extreme conditions, mud, gravel, snow. Built with deep tread blocks for maximum traction. Require extra reinforcement to prevent punctures. DI performance and racing tires. Produced in small batches with handcrafted precision. Slick tires for maximum dry grip, grooved versions for wet conditions. Rapid wear rate due to soft compounds, requiring frequent replacement. E. Aircraft tires. Built to withstand extreme loads and temperatures. Made with multiple reinforced plies up to 30 layers. Tested under high-pressure conditions for reliability. For emerging technologies in tire manufacturing. A. Airless tires, non-pneumatic tires, NPTs developed by Michelin, Uptis, and Bridgestone. Puncture-proof design eliminates the need for air pressure. B. Smart tires, IoT-enabled sensors, real-time monitoring of air pressure, tread wear, and road conditions. Used in advanced fleet management and autonomous vehicles. C. Self-healing tires, experimental rubber compounds that repair small punctures. Inspired by biological regeneration techniques. DI. Sustainable materials and recycling. Use of recycled rubber, soybean oil, and bio-based fillers. Companies like Goodyear and Continental investing in green tire production. E. 3D printed tires. Future concept allowing for custom tread patterns on demand. Enables rapid prototyping and specialized performance designs. 5. The future of tire production. With the rise of electric vehicles, EVs, and autonomous driving, tire manufacturers are shifting towards low rolling resistance designs for increased battery efficiency. quieter tread patterns to complement silent EV motors, adaptive grip technology that adjusts to road conditions dynamically. In-depth look at tire production and industry innovations. Tire manufacturing is a highly sophisticated process that involves engineering, chemistry, and precision machinery. Various tire types ranging from passenger car tires to aircraft and off-road tires are produced, using specialized techniques to meet different performance requirements. This deep dive explores every aspect of tire production, from raw materials to future advancements. 1. Key raw materials in tire production. Rubber compounds. Tires are primarily made from rubber, which can be natural or synthetic. Natural rubber, sourced from rubber tree plantations, known for elasticity and durability. Synthetic rubber, derived from petrochemicals, with variations like styrene butadiene rubber, SB, enhances wear resistance. Butyl rubber, used in inner linings for air retention. Filler materials for strength and performance. Carbon black and silica, improve wear resistance, durability, and traction. Clay and silane coupling agents, help rubber bond with silica for better wet grip. Structural reinforcements, steel belts, provide rigidity and puncture resistance. Textile plies, nylon, polyester, aramid, Kevlar, ensure flexibility and impact resistance. Chemical additives, antioxidants and antiocyanins, prevent cracking and oxidation from UV exposure. Sulfur and accelerators, essential for vulcanization, hardening of rubber. 2. The tire manufacturing process, a design and development. Tire production begins with extensive research and development, using CAD modeling and AI simulation. Predicts how tread patterns affect performance. 3D printing, prototyping, rapid testing of new tire designs. B. Rubber mixing and preparation. Raw materials are blended in Banbury mixers, creating different rubber compounds for treads, sidewalls, and inner liners. Rubber sheets are formed through an extrusion process, shaping them for later assembly. C. Tire component preparation. Various parts of the tire are prepared before final assembly. Inner liner, air retaining rubber sheet, carcass body plies, layers of textile reinforced rubber, beads, steel wire rings wrapped in rubber, for a strong rim connection. Tread and sidewalls, extruded rubber strips for traction and durability. DI tire building, a tire building machine assembles all components layer by layer. Inner liner and carcass layers are placed first. Beads and sidewalls are added. Steel belts and tread layers are positioned for strength. The result is a green tire, which is unvulcanized and soft. Curing and vulcanization. The green tire is placed inside a curing mold and subjected to heat 300–400 degrees Fahrenheit, and pressure. Sulfur and accelerators bond rubber molecules, hardening the tire while forming its tread pattern. Branding, grooves and textures are also embossed in this stage. F. Quality control and testing. Every tire undergoes rigorous testing to ensure performance and safety. Visual inspection. Checks for defects like air bubbles or cracks. X-ray scanning. Detects hidden structural flaws. Uniformity and balance testing. Ensures smooth rolling. Tread wear and durability tests. Simulated road tests under various conditions. 3. Types of tires and their specialized manufacturing techniques. A. Passenger car tires, mass-produced with automated assembly lines, designed for comfort, fuel efficiency, and wet-dry traction. Includes all-season, winter, and high-performance variants. B. Motorcycle tires, precision engineering for lean angles and high-speed stability. Many feature dual compound, construction hard center, soft edges, built with bias-ply, flexible, or radial rigid structures depending on usage. C. Off-road and agricultural tires, large thick tread blocks for deep traction, reinforced with extra steel belts and multiply layers to resist punctures. Specialized curing processes for extreme durability. G. Racing tires, Formula 1, MotoGP, etc. Manufactured with handcrafted precision for optimal grip. Slicker grooved tread patterns designed for specific weather conditions. Soft rubber compounds provide maximum grip but rapid wear. Aircraft tires, constructed with 30 reinforced plies to withstand extreme loads, capable of enduring 200 miles per hour landings and thousands of takeoff cycles, filled with nitrogen to maintain consistent pressure at high altitudes. 4. Advancements in tire manufacturing. A. Airless and non-pneumatic tires, NPTS, Michelin Uptis, Bridgestone air-free concept, puncture-proof honeycomb structure, reduces waste and eliminates the need for air pressure. B. Smart tires with IoT sensors, embedded pressure, temperature, and wear sensors. Helps fleet vehicles and autonomous cars optimize performance. C. Self-healing tires. Uses microcapsules filled with liquid rubber that seal small punctures automatically, inspired by biological self-repair mechanisms. D. Sustainable and recyclable tire materials. Soybean oil, dandelion rubber, and bio-based resins replacing petroleum-derived rubber. Continental and Goodyear leading efforts in 100% sustainable tires. E. 3D printed and customizable tires. Goodyear recharge concept, modular tread that can be replaced with biodegradable cartridges. Enables instant customization for road conditions. 5. Challenges in tire manufacturing. Despite technological advancements, the tire industry faces challenges. A. Environmental impact. Over 1 billion tires are discarded annually, contributing to waste. Efforts to improve recycling and reduce carbon footprint are ongoing. B. Rising raw material costs. Natural rubber shortages and fluctuating oil prices impact production costs. Manufacturers are researching alternative rubber sources like guaiol plants. C. Meeting EV tire demands. Electric vehicles, EVs require low rolling resistance tires to improve battery range. Special tread patterns are being designed to reduce road noise, since EVs are quieter. 6. The future of tire production. Tire technology is evolving alongside the automotive industry. Autonomous vehicles. Smart tires with real-time diagnostics will become standard. Adaptive tires, capable of changing tread patterns based on weather. Fully sustainable tires, targeting zero waste and fully recyclable materials by 2050.